Hey, can everyone hear me? Yeah. Okay, so I'm going to be talking about using beam simulations to model mutual coupling coefficients. So you might have heard Miguel mention briefly that mutual coupling is not an issue for the MWA, and I am trying to show whether or not that is true. So first of all, we have that the general, why haven't we detected the EoR yet? We have that the 21 centimeter signal is very faint. This is a graph of the current limits in theory, and a lot of those limits are because of instrumentation uncertainty, and especially the beam pattern is a main uncertainty, as was mentioned a couple of times earlier. So really, bottom line is we need to understand our instruments extremely well so that we can actually get down to those theory lines. So I've been working with MWA, specifically the phase 2 compact configuration, and specifically the 2 hexagonal subarrays. So that's the 36 tiles forming one of those. And the reason focusing just on this is because that is more sensitive to the 21 centimeter signal, the short redundant baselines that form that hex. And that's, again, really important, trying to get down to that signal. Kolopanis et al., the 2023, found a strong common mode signal in the phase 2 data. So you can see it here. But it's not in every baseline. And so some baselines did not have that strong line there. And this introduced a statistically significant bias. And short baselines, again, are the most sensitive to EoR. And previously, all short baselines were flagged. And now trying to, in the process of bring all of those short baselines back into the data set, this common mode signal meant 50% were still flagged out. So that's not ideal. And this was what prompted the decision to start looking into mutual coupling and other things of just generally what would be sources of this excess correlation that we're seeing in the phase 2 data. So a general overview, you have your sky signal, that astrophysical radiation is coming down and hitting your array. And some ways that you can get excess correlation is you can have antenna to antenna reflection, which is where that sky signal bounces off of a nearby antenna. You could have an outside radiation source. So this could be a loose connection to a receiver. It could be a nearby microwave going off, something that is causing that. Then you could have re-radiation, which is where you have your sky signal go into your antenna and then it is bounced back out and re-radiated out to the rest of your array. And then you could also have an outside reflector. So this could be shelters, it could be bushes, it could be anything else that is just reflecting that signal. But what I'm mainly focusing on is this re-radiation. So re-radiation is a part of mutual coupling, and we want to understand how much does mutual coupling actually affect the MWA visibilities. And I'll also be touching on trying to model the antenna reflection because that's another part of mutual coupling. So using a couple different models for mutual coupling. The first one is a numerical EM simulator. Specifically, I'm using FICO. So the benefits of using a model like this is you can make a very detailed model of the antenna. You can have multiple paths for excess correlation, specifically for our purposes, direct re-radiation and re-radiation reflection, which I'll explain in a minute. But it can be very time-consuming and computationally expensive, especially if you're running FICO on a single lab computer that regularly crashes. Makes it very difficult to build up complex models. So another model that I can use is a re-radiation model, just mathematically. So it's simplified. I only need to run a FICO simulation for one antenna instead of a whole array of antennas. This also makes it very fast and easy to scale up to the size of an entire array, but it only models single path for excess correlation, only the direct re-radiation. So what this means is that if you have a subset of tiles and you have one of them is re-radiating to all of the tiles around it, you get direct path re-radiation, which is directly reading the radiation that is coming from that tile. But then you can also have reflections. So we're still trying to see how much excess correlation is getting into that top antenna, but that re-radiation can bounce around and bounce from the other antennas. So it's not the sky signal that's getting reflected, it's that re-radiation that's getting reflected around your array. So this is the multi-path re-radiation. When it comes to choosing, again, trying to scale down to make simplified models that I can actually run in my lab, choosing the baselines, going back to Kolopanis et al., they looked at 3 baselines, 14 meter, 24 meter, and 28 meter. And this is because they're the shortest baselines, they're the most redundant, and therefore the most sensitive. And so I specifically looked at modeling the 14 meter and 24 meter baselines. So building up the multi-path re-radiation model in FECO, I made my model to be the same as what was used in the 2016 FEE beam model. So the model has an LNA and a voltage source, and the entire array is north-south polarized. So this is an image of one tile with 16 dipoles, and that little blue orb is the LNA being shown. So this is the 3 different tiles in the 2 different configurations, 14 meter and 24 meter baselines. And then this is the path of the S parameter, or the mutual coupling that I was looking at. So it's going to get complicated. That's why I have these diagrams with labels of basically looking at the mutual coupling between tile A and tile B when there's a 3rd tile present. So you're going to be getting coupling coming from that. And then same for the other tile. So what you end up with when you're actually measuring how much excess correlation is coming, for the 14 meter, we get that the coupling between tile A and B is the highest at between 40 and 30 dB. And then the other 2 are significantly lower, which, following symmetry as well, they are almost identical. So this follows what we would expect, that for direct line without adding trigonometry of diagonals into the equation, you have 2 different lines that are still mainly controlled by the shape of your beam. For the 24 meter baselines, the levels are much lower. So again, when you've got the amplitude across frequency, it's controlled by the shape of your beam, but it is at a lower level because of the fact that you have longer baselines. So when we compare the 2, this is the mutual coupling, the amount of mutual coupling across frequency. It's going to be much higher at shorter baselines, which makes sense because the re-radiation is not having to travel as far. But you can still see it's on the level of minus 50 to minus 30 dB, which still seems to be a lot of excess correlation that you could be getting, but is that still too much for us? So looking at the single path re-radiation model, Rath et al. Defines the visibility equation with mutual coupling as this, where you have your original or ideal visibility, and then you are multiplying in a mutual coupling coefficient to get your modified visibility, which is including that mutual coupling in it. And to calculate the coupling coefficient, we need the wavelength, reflection coefficient, beam area, frequency, baseline length, and the far field radiation pattern. So I'm able to get the reflection coefficient, the beam area, and the far field radiation pattern from FECO for just a single tile. So putting all of it together to try and build it up, we get, just looking at a single 14 meter baseline, we have our reflection coefficient, the wavelength over the baseline, the exponential, which is just a line, 1 over the beam area, our far field radiation pattern, and the coupling coefficient. So we can see that definitely the coupling coefficient is dependent on the shape of your beam and that far field radiation pattern, which is going to have an effect on not only how much mutual coupling you're seeing, but also as you're moving in frequency and as you're changing the direction that you're looking, then you're going to change the amount of mutual coupling that you're seeing. But when we compare this with the multipath that I had been showing earlier, we can see that the re-radiation model is much lower. It's about 20 dB lower estimation of mutual coupling. So the question is this the issue of having the reflections that the re-radiation model is not accounting for, or is this something else going on and we need to modify the re-radiation model because it's not actually capturing what needs to be included in this coupling coefficient, or are both models wrong? We don't know, but I could keep going through many more plots like this. I have many plots, but really, why does any of this matter? And we have to go back to the original question, which was, how much does mutual coupling affect the visibilities? And do we need to be worried about it? That's the thing. If we don't need to be worried about it, then none of this actually matters. So we can make an approximation using the re-radiation model of the total amount that mutual coupling will affect the visibility. So if we go back to this equation and we approximate this ideal visibility to be identical for all baselines, which we know that that's not true, but this is an approximation. So we approximate it to be the same for all baselines and that the indices are interchangeable. We can sum for every mutual coupling coefficient. So we have our worst case scenario is this, where all I need to calculate is the coupling coefficient for every single baseline and then add them together, and that will give us essentially a percentage. So using limits from Trott et al. 2020, we approximated a limit of minus 20 dB for the visibilities, that we need to be lower than minus 20 dB for this sum. So doing the re-radiation model, we get this, which is a plot of if we're measuring from this tile and we calculate the coupling coefficient between every other tile, with the numbers being the length of the baseline, we start seeing the beam pattern. We get the actual shape of the MWA beam, and we can see that the location of nearby tiles is more important than the baseline length, because we can see these two baselines are both 14 meters, but this tile has much higher mutual coupling occurring than the other one. And then if we change the tile, so instead of measuring from a tile at the edge of our hexagonal array, but look at one that's more centrally located, you can see again even higher mutual coupling coefficients surrounding it. And so we can get this, where again we can see the shape of the beam that is affecting the mutual coupling. And so when we sum all of these coefficients together, for the case where the tile is at the edge, we get this pattern where we're plotting the red dots are the sum of all baselines, whereas the dashed black line is just for that 14-meter baseline. And then that line across the top is at that minus 20 dB level that potentially is where we need to be below. So we can see that when you're summing all of the mutual coupling coefficients, we are about 5 dB higher than if you're just looking for a single one. But it's only at high frequencies that we start approaching that theoretical limit line. And then even when we move to a middle tile, now we're getting even higher levels of mutual coupling because there are more tiles nearby. It's still only at high frequency that we are approaching that power spectrum upper limit line. So this is with both of them together. You can see that the sum is still higher than for just a single tile, but it's still below that minus 20 dB. So summarize, we need to know how much mutual coupling affects the visibilities. Our models show that adding more tiles does increase the amount of mutual coupling. We need to come up with a rough approximation for how much mutual coupling is near the EoR spectrum limits. And it's showing it's only at high frequencies, but our open questions are, why is there a 20 dB difference between the two models? And is that minus 20 dB the actual EoR power spectrum limit that we need to be under? I will leave this up here and take questions. And I know that Miguel is going to be asking me questions I don't know the answers to.
I realize, I guess, and I'm a little unclear on limit, the minus 20 dB limit, but my mind had two versions of it. One version was, given the limits we already have, you know that the coupling has to be below a certain value. And another version of this is the level the coupling would have to be to not keep us from observing the EoR.
Yes, so this is looking at the current 2D power spectrum limits with EoR models of what does this need to be below to not contribute to more contamination in the EoR window.
Any other questions? Yes. Yeah, great talk. Thanks very much. The SKA, our team are doing full video models of SKA stations, 6 antennas, and just starting to do video simulations of two adjacent stations to look at the interstation mutual coupling. So, yeah, and they're doing that on pretty big HPC facilities. I guess if you wanted to have us run a video model for you on this basis, that should be no drama.
Yeah.
So, chat about that. And my question, this assumes uniformly performing electronics, LNAs, everything. Does your upper limit still hold if some fraction of the antennas LNAs are misbehaving in some way?
So like I said, this is a worst case scenario where everything is functioning exactly as we expect. Ideally, everything is the same. This would be the maximum. So if, for instance, something is going on with an LNA where we're not getting as much coupling between antennas, then that would bring this, the mutual coupling level down. So yeah, this is very much an idealized model of everything. Also assuming every antenna has the same reflection coefficient, that everything is built exactly the same. And we know that that's not necessarily true. So. Thanks again, Catherine. Our next speaker is it's all about harnessing deep learning to map nickel hydrogen during transition.
Are you going? Yeah, I'm almost there. We'll get you there. Thanks. Good. You just click on. Yeah. Hello, everyone. So I'm Michele Bianco. I'm postdoc at ETH in Zurich. So today I would like to present how we can use deep learning to try to learn something about the organization. And this was a project developed also when I was at PFL, and maybe you recognize a few people from the name that help in these works. So yeah, so just that in the middle, right? Here we go. I went. Okay. So just to put, so that we're all on the same page, I mostly focus on organization, and this is the period that we expect to, let's say, this transition of the early universe that we expect between Redshift 20 and 7, and this is actually the goal of the ongoing and future, interferometer experiment from which MWA. But, and I put these slides just to remind myself to say that I mostly focus on my work mostly focused on SKLO, but hopefully some tools that we are developing, it's also useful for MWA. Why? So SKLO in principle will be sensible enough not only to detect the signal, but also to provide images, redshifted images of the 21 centimeter signal. So that, you have this 3D data set that on the XY axis is give you a location in the sky, and the third is going to give you either redshift or the observed frequency. And so that we can basically see the fluctuation of the 21 centimeter throughout realization. So there are ongoing observation that are providing mostly upper limits, and a few of these upper limits are actually provided by MWA. But as you can see from, let's say, the theoretical expected signal, we are a few order of magnitude off. And most of you are probably well aware that this is because we have a few things in the way of detecting 21 centimeter. And actually the most annoying one personally is that, the foreground contamination, which can be up to 6 order of magnitude larger than the signal itself. Right. So this, let's say, this problem basically inspired us to develop some machine learning application. And so through the years, we put together a bunch of neural network, and we created Session3, so it's French pronounced because it was here in APFL, for segmentation and recover network. So basically, this is the pipeline of our let's say, of CERNet. So we start from some image that is contaminated by foreground noise. We are still limited in a sense that we need to apply pre-process steps so that we take away most of the largest contribution of the foreground so that we get a residual image. And then we have these two networks. Now one is SegUnet for segmentation of image. So this is is going to basically tell you in which portion of the sky we should expect H1 rather than no H1 at all. And the second one is RecUnet. It takes these residual images and these binary maps and try to recover the 21 centimeter signal. This slide is just a detail, but I like to put it just because there is, in case you wanted to, the GitHub, and wanted to mention the paper is going to be out soon, as a matter of fact, next Monday. But we created, especially for RecUnet, the reconstruction of the 21, we created this type of network that has these intersection convolutional blocks and basically allowed for an additional input that we like to call the binary prior, which is this segmentation map from before, right? Yeah, and is just I want just to mention that we participated at the SKA Data Challenge Part A that was focusing exactly on this, so removing foreground. These were the people that participated, and I was at APFL when this happened, and we arrived in the top 10. That was great success, personally. Anyway, okay, so this is just a look out of what the input of CERNet are. So we have the residual image on top. Then we have, well, the ground truth that the network train on. These binary maps, that we we predict image by image, but we can put it together to create the tomography data, and then we have the the predicted the predicted oh, there is a typo, a predicted 21 centimeter signal on the bottom. As I said, I'm mentioning this because later it's going to be useful. So we are still limited by standard pre-processing step. For the moment, we have testing which one is giving the best residual image, because this will just make the life easier for the network. We have standard PCA decomposition, wedge removal, GPR, or simple polynomial fitting. And on the bottom, you just see the corresponding power spectra centered at that redshift with that specific frequency range. Right. Okay. So a first look of the results is of SegUnet, just to mention that this was the results of a separate paper. Now we construct on top of that. So these are the kind of output that we get, these binary maps in blue and red, and then the contours show just the ground truth to give you an idea. And what we are able to do with this type of network, we try from the image to recover the volume average neutral fraction, which is this factor that tells us what is at which stage of ionization we are. Okay, and the color indicates the redshift of these images. So this was performed on a large testing set that we used to statistically quantify the effect. Right. Then we moved to CERNet. So we use the residual image and the binary prior on this very large field of view of 10 degrees, which is more or less what we expect from SKLO. Has 900 frequency from that specific frequency range. And this is very similar to the, let's say, data provided by the data challenge. So we create our own data from the data challenge description. Right? And what we are able to do, you might see there is a zoom-in region, but what we are able to do is to recover this 10 by 10 field of view. On top of each column, we have some sort of score that will come in the next slides that qualitatively tells us how good is the reconstruction. And on the left, we just show the corresponding predicted power spectra, 2D power spectra. Right. So we evaluate this on a statistical level. We look at this score that astronomically doesn't have a lot of meaning, but for the purpose of understanding how good is the network doing and where, it's kind of, okay, I can indicate that. It's kind of helpful. So we look first on how good the network work compared to the, which stage of ionization we have. Let's say the fallout that you have at the, let's say the true extreme case, early stage and late stage of ionization. This is mostly due to the pre-processing. So here we're using PCA, and this fallout is mostly due to the unsuccessful decomposition of PCA. But overall, what we can say that we obtain quite a high score, and the plot on the right instead is showing us the relation between the accuracy in the 21 centimeter image versus on the x-axis the accuracy of the binary maps, right? So this is basically a way to understand if the binary prior is actually giving advantage or not. And what we can tell is that we can see first the blue color indicate late stage of ionization. So in this case, the binary prior actually do not give any additional information, is actually working against the reconstruction. This is because we expect the maps to be mostly completely ionized. So it's basically providing no useful information in their construction. And then at the same time, on the opposite case, when the maps are mostly neutral, the binary instead is kind of misleading the prediction, because it's basically suggesting to take every region in consideration. Okay, so this is a limitation that we will try to explore. Then small details, but interesting. I added these at the very last moment because someone talked about the synergy, let's say, between SKLO and Galaxy. Oh, there is an Error? Okay. This was supposed to say galaxy prior, and this is actually with no prior at all. So what we do here is, because we are doing simulation, we have the position of the sources, which is represented in these red dots. So based on their position and on the some assumption on the mean free path, which is tell us more or less at which distance the photons more or less can travel. This is you can see an example with the small green sphere for the most massive sources that we have. So basically what we can create is this sort of binary maps in cyan color that we can now, with some binary, we binarize this field. And so basically what we can do is use this galaxy prior to the network and to see if it's give meaningful results. And what is surprised to find is that no matter, I mean, as the title suggests, any prior is better than no prior in a sense. That even though the prior from the galaxy is not perfect, is still helping to kind of recover the 21 centimeter. Oh, they are missing some, no, okay. Anyway, then one detail about the pre-process, we are now considering use another pre-processing. In this case, we are focusing on the Bear estimator, which was developed by Chaudhuri in 2024. So the assumption is that, well, if you assume a certain model for the angular power spectra of the foreground, we can look at the correlation between visibility, and basically what we have, well, we first have some constants that are mostly defined by the primary beam. Then you have, well, the distance between these two visibility, but the noise, of course, and then the angular power spectra that we would like to quantify. So this was the project of a master student and now is finishing. So looking for the next person to take over. But one result that we did is basically we simulated some galactic synchrotron foreground, and we look for SKLO, and specifically asking also for MWA for this meeting. And what we basically can say is that we are employing this Bear estimator and try to see what is the quality in the residual image. So how if CERNET can in principle process this type of image. Right. So these are his preliminary results from the thesis. So based on the model, we did some MCMC inference, and so that we can in principle quantify the parameter of the angular power spectrum, and then we can in principle subtract it. I see something went wrong with my summary and to-do list. So I leave this, there is a lot of things to do, but unfortunately I'm not sure. But yeah, sorry for this, I take question if. Yeah, I guess Google slide is not.
To do the slide.
Huh?
To do the slide.
Yeah, to do ever.
Questions? On your prior to
This one, yeah.
Aren't you afraid that your prior is just a neutron and it gives too much of it on which way it's training? Space between.
Yeah. Yeah, I don't, I have not mentioned, we did not retrain the network on this. So we trained the network on this, this sort of prior that come from the Nelson fraction. And we wanted to see how bad the prior can be and still be better than having no prior at all. So of course, the major issue is what is the assumption on the mean free path. And there are specific redshift in where this assumption holds and works relatively good, and some cases not. So this was just, let's say, a test for us, but we should look more in detail.
Questions? Come a little bit
I have a question, I guess. So, we're always a bit worried about overfitting with these deep learning techniques. Have you tried this with like a completely different realization model that like the network's never been trained on?
Yes. Yeah, as well. Okay, so you.
Or like a different.
Yeah, we tested on a different way of simulating the 21 centimeter. So these simulations are done with the semi-numerical code, and we wanted to see if we do a if use a fully numerical code, it does still work. In principle, yes, but we probably should change in base also the cosmology. It's true that here we always assume a fixed cosmology. We focus more on the astrophysical parameter, but I don't think it's gonna hold for a different cosmology.
So we'll check.
Most likely, yeah.
Any last questions from the audience? Okay, thank you.
Remember to do a PDF next time.
Our next speaker is Kathy Singh. We'll be talking about mechanics, the organization of
Oh, sugar. Damn, I just got rid of WebEx. Oh, it's come back. Cool.
15 minutes. I'll just be sitting in the corner there, so I'll give you 10 minutes. We've got 10 minutes left in the corner.
Sure. Just click in the middle to get the page.
Okay, good afternoon, everyone. I'm Kathy. I'm from Shanghai Astronomical Observatory. Well, I'm happy to be here today to give the talk on behalf of all my collaborators. It's okay. Okay. And my topic today is a candidate field for deep imaging of cosmic dawn EoR with the MWA. Okay, we know that deep imaging of the EoR of a few selected fields is one of the key science goals of the future SKA. But because the 21 centimeter signals of the EoR is very weak and deeply buried in the foreground and the noises from the instruments, so it's very hard for us to deal with the data reduction and the foreground removals. So I think that if we can select a few candidate fields without very bright sources and bright large-scale diffuse structures, it will reduce our difficulties in the data reduction and foreground removals. So using multi-frequency observations, we tried to select a few candidate fields. And the size of the field is decided by, in our selection, is decided by the largest ionized structures during the late stage of the EoR. So we also consider the simulated SK beam pattern. Well, in this, can you see? No. Not sure if you can see it. In the plot there, it presents the distribution of the massive galaxy clusters, and in the plot, in the figure in the bottom, the small circles are our selected EoR fields, and the bigger ones are the 3 MWA EoR fields. And then in the past few years, we tried to do some observations with MWA of a few targeted fields using both of the extended configuration and compact configurations. And for the project D0018 and G0091, these two observe the same sky regions. So currently we are working on this data. We use the extended configuration data sets to study the foreground properties and the sky models. For the compact configurations data set, we hope to do some statistic study of the background signals, but currently we are still struggling with the calibrations, so I don't know what will happen. And for the D0013, mainly we use this one for testing some pipelines and to study some foreground sources. And M87 is one of the example we found in that sky regions. And G0044 is the sky region we are talking about today. And it's one of our selected EoR candidate field. And the observation was done in the year 2018 and used the extended configurations. So of course, we are not going to do it. We do the EoR study with this sky with this extended configuration data set. We just want to study the foreground properties in that sky regions. And we will observe 5 gleam frequency bands because it will be easy for us to get rid of the strong RFIs. So currently, we finished the reduced data of 2 frequency bands, 87 and 215 megahertz. And about the integration time for each snapshot is 2 minutes. And for the 87 megahertz, we have 169 snapshots can be used. And for the 215 megahertz, there are 133 snapshots can be used. And then that's the, in the bottom, we present the center region we use to produce all the images. And the image here is a combined image of 30.72 megahertz, and the center frequency is 87 megahertz, and is 20 by 20 degrees. And when we talk about foreground removal, I think it's important for us to understand the smoothness of the spectrum of the sources in our sky regions. And we try to use some catalogs to study, to look for the sources with spectral peak, and then using simulations where we want to study the influence of these kind of sources in the EoR detection. And the conclusion for our published work is that they won't affect the final result of the EoR detection. But in fact, there are some limitations of this work because we didn't consider the galactic emission. And also because it's based on simulation, the real situation will be more complicated. So in the bottom plot, the blue points are all the sources with spectral peak, and the orange ones are the bright sources above 2 Jansky at 150 megahertz with spectral peak. And the 7 fields are our 7 selected EoR fields, and the G014 field is mostly overlapped with one of our selected field. And we see that in the center region of this field, there are no bright sources with spectral peak. And understanding the smoothness of the spectrum of the sources in that sky region will help us to find the proper method for the foreground subtraction. And here, because it's extended configuration, we mainly adopt the pipeline demonstrated in Stefan's paper, and it's done by a postdoc in our group. And it's similar as the pipeline used in the gleam data reduction. And for this data set, currently we just did some statistic study of the sources in that sky regions. And here the plot will present the source number counts of the 2 frequency bands, and the 87 megahertz and the 215 megahertz. And we use different integration times from the 10 minutes to the maximum time we obtain from the observations. And we take 5 degrees radius around the field center as the sky region for our study. And we found more than about 2,900 sources. And as we expect that when we increase the integration time, more faint sources can be detected. And this is related to the confusion noise we can obtain in the final images. And then we tried to compare our source completeness with the SK simulations. And we use agent to select the sources. And we use 5 sigma and 3 sigma of the background noise as the parameters for the source selections. And also we calculate the differential number counts of our sources in the images, also for the different integration times, and make comparison with the Gleam survey. Well, for the 87 megahertz data set, we found the spectral started to drop down at about 0.04 Jansky when the integration time is about 18 minutes. And for the 215 megahertz data set, from this spectral, we found there are no big differences between the integration time is 18 minutes and 206 minutes. And the spectral is flat, keeps flat until the flux is about 0.01 Jansky when the integration time is about 18 minutes. And then we tried to do some foreground subtractions with this data set. So currently we present the result of the 87 megahertz observations for all the snapshots, about 169 snapshots. And we adopt the principal component analysis. And we use WS clean to split the data set into 4 frequency channels and to make some comparisons. And here we present the result of 1 frequency channels. The left one is original image, and the middle one is the PCA subtracted foreground components. And the last one is the residuals after the foreground subtraction. Well, in the sky region, we tried to remove foregrounds. For the combined 30.72 combined image, there are about 461 sources can be detected. And for the PCA subtracted 4 sideband image, we present the percentage of the sources can be subtracted comparing with the combined image, because the quality of the sideband images are not as good as the combined one. And later, we are going to try other maybe frequency band sidebands and try make plot of other frequency channels. And of course, the PCA method here is currently based on the images. And maybe in the future, we are going to try some other methods working on the UV data. Oh. And here we present the power spectrum, just a rough estimation. And the left one is the PCA subtraction with different PCA parameters. And for the right 4 plots are the angular power spectrals of the 4 sideband images. The bottom gray lines are the estimated EoR signal, and the blue ones are the original data, and the orange ones are the residuals after the PCA subtraction. Well, I found there's a turnover in the residual power spectrum, but because we just got this spectrum last week, so I didn't have time to find the reason. I don't know why now, so going to check it later. Well, currently, I think our calibration still needs to be improved, and maybe PCA is not the best method for the foreground removal at the moment. So maybe I still think that maybe it can still be improved. So we give a rough estimation of the final noise we can got from the images, including the thermal noise and the confusion noise for the 4 frequency channels. And for the thermal noise, we consider the maximum observation time, and we also consider the 500 hours observation time. So for the 215 megahertz data set, we found our confusion noise is almost at the same level as the thermal noise. And we use the number counts derived from our current estimation observation to estimate the confusion noise and thermal noise for the future SK load. Of course, the confusion noise is dominated. But for the future SK, I think the resolution and sensitivity will be much better, and the confusion noise will be lower than our current estimation here. Well, here's the conclusion. Well, currently we are still working on other data sets we applied with the MWA and using some pipelines like hyperdrive and other things to try to do some calibrations. It's still a long way for our group to go. Too many black boxes for us. Well, thank you. Yeah.
For the single free.
We do PCA on the full frequency band.
I'm curious as to whether you think the effect is the ionosphere, especially at the lower frequency that you were using. So the increased brightness of the ionosphere at lower frequencies would also mean that you would probably get a sort of scintillation of these sources at the lower frequency, right?
Yeah.
So did you take that effect into account?
Mm-hmm. We just adopted the pipelines used by Stefan's paper, and we didn't use the direction-dependent calibration at the moment. So maybe we need. That's why I said our calibration still need to be improved in the future, because we found our data reduction of the 200 meters data set and frequency is much higher. We get better results. And so for the 81, the result is not as good. That's why I selected two frequency bands to reduce at the moment.
Other questions?
Is your confusion noise unresolved sources or side load confusion, or is it all sources of confusion?
Well, the confusion noise we calculate at the moment, I remember when we choose the limit as the something like lower than 20% of something of the sources can be absorbed. It means more than maybe that level related to the plot, like something like more than 80 sources cannot be resolved at that flux limit.
We have time for the question. That's it. Yes. Okay, if not, then it's. Steven Krishna will be talking about excision with bright point source visibility to 21 centimeter data.
Oh, okay. You put me on the spot here, aren't you? Let's probably this drive, scan the drive and fix it.
Don't scan.
Continue that scan.
Oh, his presentation is already in that.
I don't know if
No,
you've had any
uploaded.
updates.
I've updated it.
This one, MWA
Yeah.
project meeting. Thanks. Share. You can put this on in the meantime if you like. Okay.
Good afternoon, everyone. My name is Shreyam. I'm a PhD student at EPFL, and this is some work that I've done in association with Michele at ETHZ, but also under the guidance of my PhD supervisors, Emma Tolley and John Paul Naib at EPFL. So first things first, we've had a lot of people talking about data today, so I want to clarify something. When I say data, I mean simulations. I do not have access to any of the MWA EoR fields as of right now, so I'm using simulations to do this analysis. Now, the outline of the talk is going to be as follows. First, I'm just going to talk a little bit about radio interferometric imaging so that you get the base that's required for the blue build algorithm. Then I'm going to talk about the 21 centimeter radio interferometric measurement equation, the 21 centimeter rhyme, then some preliminary results, and then some future scope of this experiment. So a single antenna in any one of our arrays receives basically a copy of the electric field of the far off source, along with a phase term, and you have gains as well, which we haven't represented here. But in this simplistic view, you cross correlate the voltages from two antennas and you get visibilities. And in those visibilities, we assume that we have our gain terms also, and we have our phase difference terms. And I am just going to represent those visibilities with this capital V and the sky brightness as this I term. So you have some additional noise as well, and that's captured here. Now, the entire name of the game in radio interferometric imaging is some sort of back projection that you have to do on your visibilities to get to some sort of best reconstructed image. Now, for this back projection, what we use is the Moore-Penrose pseudo-inverse. And this basically takes into account the sampling operator, which is basically everything that's happening that's changing the original signal in the sky when it's measured by the antenna. So it's the sampling operator. And it's basically taking the sampling operator and its own Hermitian inverse to make this formalism of how we reconstruct the image. But in this formalism, you have these pesky inverse terms, these G psi inverse terms. And these are often ill-conditioned and difficult to invert. And so what we really want to do is we want to reproduce our images in some sort of an optimal way where we can sum our images using some sort of eigenvalues like this. Now, what we do is we achieve this by eigenvalue decomposition. The blue build algorithm basically frames a generalized eigenvalue problem for your visibilities and decomposes your visibilities into eigenvisibilities sorted by energy, sorted by brightness, essentially. So the eigenvector along with the sampling operator gives you your eigenfunctions. And these eigenfunctions give eigenimages, which are independent and, like I said again, sorted by energy, or in this case, brightness. These can be filtered. So originally, when the algorithm was, when people came up with the algorithm, the idea for this was to do automatic noise filtering. But in radio astronomy, the noise is actually quite useful to us. So this filtering, in our case, can be used for removing brighter sources rather than removing the noise. Fundamentally, the algorithm does two things. It does an eigenvalue decomposition of the visibilities, and then it reconstructs those visibilities on the sphere using a type 3 NUFFT. So there is no W approximation of any kind done, and you reconstruct visibilities directly on the sphere. And just to give you an idea of what this looks like in practice, let's say you have this one image of there are 4 Gaussians in this image. I promise there are 4 Gaussians. I'm not just saying that. There are 4 Gaussians in the sky model of this image. And you can only see one Gaussian right now because of the brightness of the primary Gaussian. On the bottom, you have an antenna by antenna matrix, which is what blue build looks at to do the eigenvalue decomposition. The color in this bottom row will correspond to the phase of the visibilities, whereas the darkness corresponds to the amplitude of the visibilities. And what blue build is doing is it's basically taking this image with 4 Gaussians and separating it out into individual levels. So your brightest sources can essentially exist in an image which is completely different from your weaker sources. And this toy example, I think, gets across a lot better than all of the equations. So let me move forward from here. And these eigenvalues that we have are basically another representation of these visibilities. These visibilities can be complementarily represented in terms of these eigenvalues, where the brightest visibility peak that you see there corresponds to the brightest Gaussian, and so forth and so on. The red lines in the eigenvalue diagram basically are telling you where the separation between eigenlevels has been made within this eigenvalue histogram. So this is the first half of my talk, which was just introducing BlueBuild. And the good thing is that we have a version of this functional that works on measurement sets. And I mean measurement sets like proper, messy, real-world measurement sets with flag data, with all kinds of interesting effects, shall we say. We have a C++ ported version, and we have MPI parallelism as well as domain partitioning inbuilt into the algorithm. There is also an HPC implementation with support for both CUDA and HIP GPUs. The one thing is there is no deconvolution included in the algorithm. We only produce dirty images. And the paper for the initial BIP release as well as the GitHub are present here. And now we move on to the second half of my presentation, which is going to be about the actual simulations that I applied BlueBuild to. And to start off, we have the 21 centimeter radio interferometric measurement equation, where we have the 21 centimeter signal in the sky model, along with extragalactic point sources and galactic synchrotron foregrounds as well. In addition to this, we have direction-dependent terms, direction-dependent gains on either side of the rhyme, and we have direction-independent gains. And to top it all off, we also have additive system noise. So while admittedly this makes for a poor approximation of the real thing, it is still, to whatever extent we have managed, a more realistic observation. A more realistic simulation, rather, sorry. The differential temperature is simulated using 21 centimeter fast at a frequency of 166 megahertz and a redshift of 7.554. These images are about 8 degrees across in field of view. And one thing you'll notice is that the differential temperature is at a level of 10 to the power minus 5 over here, compared to the foregrounds, which are about 10 to the power minus 1, compared to the extragalactic point sources, which are at about a unit level. The point sources have been taken from the Gleam catalog. The galactic synchrotron emission has been taken from Tools 21 centimeter, which in turn uses a model from Ghara et al. 2017. Now, these visibilities have been generated using the SK low configuration on Oscar by utilizing the Carbo pipeline. This is a 4-hour long observation, so it's about 17 gigs, the MS file that is produced. It's 100 kilohertz in bandwidth, so each frequency that's produced is 100 kilohertz in bandwidth. And like I said, this is a realistic simulation in that we've added ionospheric effects, additive noise, and direction-independent gains. But I still think that based on everything I've learned so far today, that it doesn't do a good enough job of approximating the actual signal and the actual complexities of the signal that we see. Now, the additive noise is added by this prescription, and the gains are basically taken around amplitude and phase, where basically we take a mean amplitude gain of 0, and we take Gaussian, we draw from Gaussian with a deviation of 0.05 around that. And for the phase, the mean is centered on 1, and we draw from a similarly sized Gaussian around that. And we have, in this time series FFT, you can see that you have correlations included in the time series itself, which is to say that it's not a completely blind Gaussian draw. One value drawn from the Gaussian is likely to be correlated to the next value. And with this, we start coming to the results part. And what you see is that first you have the eigenvalue histograms representing our different data sets. You have the differential temperature in the red here. You have the extragalactic point sources in the pink and the galactic foregrounds in the blue. And on the right, you have the same thing, but now all added together. So you have the galactic foregrounds along with instrumental effects, along with differential temperature and extragalactic foregrounds as well. And we try and separate out the bright point sources from this prescription. And this is the eigenvalue histogram we get for the case where we don't include instrumental effects. And going to the actual images that we get, what you see is that you have, again, the least squares image, which is the net total image that you would get, but you also have your eigenlevel images. And in the eigenlevel images, your bright sources start to get separated periodically, depending on their flux. And what starts to emerge underneath is the galactic foreground. Similarly, the same happens for the case where we include instrumental effects as well. Again, we see that the bright sources start to get separated. Again, this is done blindly. So all I do is I run the algorithm. I tell it that I want 7 eigenlevels, and it separates them out into these 7 eigenlevels. I can, in principle, cheat and say, I know the highest eigenvalue of the differential temperature brightness, and I want everything above that to be in a completely different level, which I want to throw away. That is possible, but just for the sake of doing this blindly, I have not done that right now. Yeah, so with that, I'll come to the end of my presentation. I'll just summarize by saying it looks like we can, at least on the simulated data set, separate out these bright sources quite well. And in addition to this, so far, everything I've done has just been on one channel. So there is no frequency correlation that's been taken into account. If you look at the eigenvalue decomposition across frequency, you can see the continuity of the bright sources. And especially if you zoom in at the lower eigenvalues, you can see these very obvious lines, these vertical lines that are basically telling you that these are the foregrounds because they are continuous in frequency. So this is some analysis that I'd like to continue on and look at the multi-frequency behavior of these eigenvalue decompositions as well. Thank you.
Thanks, Shred. Questions?
It's a question, but I think it's the idea was if we were to look at like one bright source in your eigenvalue decomposition, does that just the source, or does that include the array twin spread function in that image? When I remove it, am I pulling out the PSF, or am I just pulling out the model?
So there's no modeling as such done over here. When you're removing out the individual visibilities, when you're making these eigenvisibilities, you're essentially decomposing the original visibilities you get into these eigenvisibilities. So in principle, you're separating it out on a PSF level as well. Each source exists, and this is something you can see also over here. Well, not here, let's say over here. The color scale isn't very good on this, but basically with a little bit more contrast, you'll be able to see that there are certain rings around these sources, and that is indicative of the PSF of the instrument. And that PSF is localized, that particular PSF property of those sources is localized to each level.
PSF is encapsulated as what the sound in the space before you apply the signal function. So in principle, yes. I mean, most of our tests indicate that as well.
Exactly.
Any other questions? Yeah.
Yeah, so many. How does this perform in the presence of systematic effects? So for example, if you had baseline-based errors in the data set, or some other similar thing, is this assuming everything's linear, noise is Gaussian? How would it perform with systematic errors in the data?
So if by systematic errors, you mean things like, for instance, in this antenna by antenna plot, you have certain antennas that are flagged. You have certain antennas that are bad. It would perform, in my opinion, the same. Simply because what it's doing is it's taking this antenna by antenna matrix and decomposing this fundamentally. So whatever you input is what you get in that sense.
Calibration errors, right?
Yes, I've also studied this. So at Swiss SK Days, which is next week, my presentation basically talks about how we look at point sources and bright point sources which are contaminating, and how we can add calibration errors to them as well. And this method still works. It still manages to separate out the bright point sources, even with the calibration errors.
Some sort of error that subset of the data that then propagates into the disabilities.
I would say so.
So in principle, though, do you think it might be included as part of the same method? But it's a question of different methods to do.
With the slide up on the screen now, this is probably the fifth time this has been explained to me, so sorry about this, but why are the disabilities not the same when you reflect it around the the waters? Why is one triangle different to the other?
When you
Oh, it's Hermitian conjugate.
oh,
Is it symmetric?
So the phase is rotated by 180 degrees, but the magnitude should be the same.
the magnitude is the same, but the phase is rotated by 180 degrees, like Emma just said. So
Maybe we need to do
yeah, I think we need to do a better job of these slides, but magnitude versus phase slides need to go in. Any more questions?
How else are you applying this to?
I've actually already applied this to MWA data. Not in terms of EoR data. I've applied this to MWA solar data to look at basically whether you can separate out the bright, centrally radially decreasing emission of the sun from the fine structure on the sun. And at least in that case, which was an MWA data set from 2017, I think, we are able to do it. We are able to basically remove the contaminating solar emission and see the solar emission that we're interested in.
Okay, questions from the audience? If not, let's take